today I just want to talk to you a little bit about some of the ways that I use crystals in my research. I like reading the crystals, and I will have a few case studies, lots of gratuitous fieldwork pictures, because whilst I very much enjoy understanding crystals, if we don't put it into a field context, the information from them is absolutely meaningless. So we need to know where we've got our samples from in order to kind of unravel the volcanic processes behind them. So maybe can't move on back. There we go. Before I jump into the science, obviously this is not just me. I've been really lucky to work with lots of people over the years, and in particular on the Cordón Caulle Chilean work with Dan Morgan, Eleonora Revolta and Luis Lara at Puyehue-Cordón. And then there's a big crew of us that have done work on Ascension Island, starting, this was back from 2014, when we ran along the runway on July the 4th. They closed the runway and there was a race, and I beat the US base commander. 10 years ago, I was much fitter in this 6K race, but it was very exciting. And there's a lot of people, and we're all kind of still working on Ascension today. So kind of what I'll hopefully try to go through is a bit about why do we care? Why should we care? Hopefully bring you all to the crystal dark side, and then give you some information about some of the methods that we can use to extract timescales from crystals. And then just a couple of case studies. So first, going to Ascension Island, an active volcano last erupted around 500 years ago, and it's a UK overseas territory. This is a picture from Ascension Island from the act we named Green Mountain. Guess why it's called that? Looking down at all of these lovely scoria cones and out to the Atlantic Ocean. And then we'll go to Cordón Caulle, Puyehue in the southern volcanic zone of Chile, just to think about the relationship between timescales and then crustal stress states. So diving a little bit out of my comfort zone, but trying to relate the information that we have from crystals, which obviously we get our hands on after the eruption has happened, to stress states, which we can measure before an eruption has happened. So some of the first steps that we took to try and understand these. So ultimately, as a volcanologist and petrologist, there are some key questions that we want to answer. And we want to know, well, what actually is this thin section going to be able to tell us? How can we use it? Importantly, the questions we get asked will be, how much warning will we get before a future eruption? That's really important, right? How much time will we have before this eruption happens? When do we need to start warning people to evacuate, given that unrest has happened? Equally, what kind of unrest might we detect before future eruptions? Do we expect to be able to resolve anything geophysically or geochemically, or might we have not very much unrest? What kind of unrest means that we're going to have an eruption versus kind of accumulate magma at depth? And then additionally, how long will this eruption last for? It's really important to evacuate people effectively, but then actually the majority of deaths from volcanic eruptions happens after the climactic phase of the eruption, because people return to these danger zones, they're not necessarily aware how that hazard evolves. And you know, if you're evacuated from the house, that's a pretty horrible condition to be in typically. And so we need to think about forecasting the duration of eruptions. And so ultimately, we want to answer the questions: when will an eruption happen? Where will this eruption happen? And how long will it go on for? How long do we have to prepare? And that's important information for the people who live close to volcanoes, but also for the people who are managing response to volcanic crises. So I'm going to put up this very well used diagram from Katy Chamberlain et al. That kind of talks about our understanding of these plumbing systems underneath volcanoes. We obviously only see these the top edifice and the eruptive products. And what we don't see is often this very extensive zone underlying the volcano that could have multiple regions of magma storage. That's what these solid colours are. They're all different magma storage regions. And there could be a very extensive mush system around them, kind of like a crystal or a magma slushy. So it's not eruptible, but it's got maybe 50% melt, 50% crystals, and it could be rejuvenated. It could be partially molten or partially melted to allow it to erupt. So we know we've got this complex storage region, although this isn't the case at every volcano, so we do need to understand individual volcanic settings. But within every single one of these magma storage regions, there's a whole load of different processes going on that can affect our magma chemistry. And ultimately, the composition of the magma that we erupt affects the hazards that are going to be produced. We know that more silicic, granitic volcanoes are more likely to erupt explosively, whereas more mafic eruptions are more likely to erupt effusively. Obviously, there's variation within that. So within every single one of these magma storage regions, we could have things like convection, or it could be stratified. We can have fractional crystallization, we can have vapor flushing, we could have magma mixing and mingling, and all of these things affect the chemical composition of the magma. So until we can understand the processes that have gone into producing the magma, we can't fully understand the potential for different hazards that we might have. So each one of these magma processes can affect magma chemistry. And I'm going to use the kind of classic total alkali silica plot, where we've got different whole rock magma compositions. And I've just tried to show how the different processes could change your location just on a simple major element plot, rather than trace elements or isotopes and so on. So we could be thinking about having magma mixing, we could have crystal fractionation, we could have changes in the degree of partial melt, and all of these things affect the melt density and the melt viscosity, ultimately affecting how that magma behaves at depth. But how do we actually unravel the recipe for magmas from its chemistry? And I always try to put a gratuitous cake picture in. I hope everyone has at least had their lunch or is having their lunch, so it doesn't make you more hungry. Ultimately, when we look at these volcanic or plutonic rocks, it's like being presented with a cake. Oh, great. But I want to know how you made that cake. And to be able to do that, we need to trace both the ingredients, but also the processes that go into making that cake. So for example, are we assembling a magma that's a product of fractional crystallization and it's just sat there and has evolved? But how long has it evolved for? If you've had all these ingredients and mixed them together and put them in the oven for 5 minutes versus 5 hours, you can have a very different flavour cake, very different flavour of magma, depending on the time and how you've let these ingredients interact together. Did you separate your eggs? All of these questions, but more volcanic related. And so ultimately, the way that we can unravel this recipe for magmas and for the production of these magmas is through looking at crystals. These are these magmatic black boxes that can record changes in intensive variables through their changing composition. So the earliest growing crystal, looking at the core, and it changes over time, just like this tree ring. And so we can have these lovely backscatter electron or cathodoluminescence images from scanning electron microscopes, where the grayscale intensity is a function of the composition of the crystal. So different grayscales, different compositions. Exactly what element is changing to produce these different grayscales depends on the type of mineral that you're looking at. But ultimately, if we can measure the concentration of these elements in these crystals, we can work out where magma has stalled. We can think about how the melt composition has changed over time, if we have melt inclusions trapped within this crystal. We can look at the changing proportions of volatiles. We might be able to identify times where magmas have come together, and we should be able to work out the temperature of the magma. Again, all of these things can affect the physical properties of the magma and therefore the eruptive hazards. But ultimately, if we can start to pin down some of these processes or these intensive variables, we can then find out when any of these things have changed. And that links back into how much warning we might get. So we can think about using the chemical variation within crystals or within melts, and then think about putting a time on when these things changed by looking at using various methods. So I'm just going to briefly go through 3 methods that we can use. The first one being crystalline diffusion modeling. This is an example of a quartz from the Bishop Tuff super eruption in California, where the grayscale intensity is a function of titanium concentration. And if we look at the contact between the light and the dark zones in our quartz crystal, we assume that at time t0, when this melt that was rich in titanium interacted with this quartz, the contact between the high and the low zones was vertical. So initially, we had a vertical contact or a vertical gradient in concentration between the high and low titanium zones in that crystal. But with time, at magmatic temperatures, and that's the key, you need these things to be hot, the crystal wants to equalize out this sharp step gradient. And so titanium from our high concentration zone will diffuse across and we'll start to widen that profile. And then with more time at time T2, we have more diffusion that's occurred and more relaxation. And so the width of this profile is a function of how much time we've let this diffusion happen for, if we can constrain the temperature. It's a big if. Okay, so we can use the width of zones, and these are on the order of a few microns, tens of microns, to help us understand when this bright rim grew on the quartz crystal. But they're all relative timescales. We're saying diffusion has happened for a certain amount of days, weeks, years. We can also collect absolute dates from minerals like zircon. I'm going to show you some zircon dates from Ascension Island, where we just measure the amount of uranium and lead, because we know that uranium decays to lead. And this can tell us when this crystal has grown. So we can use things like secondary iron mass spectrometry or laser ablation ICP-MS to collect ages of these crystals. And so these are absolute ages. We're not messing with these. We're not saying how much time has happened for this process to happen. And then finally, slightly more qualitative at the moment, we can look at diffusion not within a crystal, but within a glass. So we can think about the very slow diffusing element. So this is two different compositions of magma that have come together experimentally. And we can see that the boundaries between high and low gradients, dark and light, are very sharp. Whereas the more rapidly diffusing element here, the lanthanum, it almost feels like you need to go and get your eyes checked because there's been more diffusion happening. So we can look at the relative contact, or at least how blurry we see the difference between two different glass compositions. And this is based on both numerical and analog models of magma mixing. So there are some kind of qualitative estimates of timescales that we can estimate based on these experiments, if they exist for the compositions that you're looking at. So, very rapid whiz through why we can get timescales, or how we can get timescales. Now we'll take a trip to the mid-Atlantic, to Ascension Island. This is the runway that I was talking about running along. And it's an amazing place, one of the most beautiful and most diverse volcanologically islands that I've been to. It's about 12 kilometers wide here, and it sits right in the mid-Atlantic. Darwin has visited, and this is his map that he created one of their voyages, and they've produced, there's no natural water on the island, and so it's they decided to plant Green Mountain, which is the highest point, around 800 meters above sea level. They brought loads of plants in, they made a cloud forest, and they've kind of concreted, the British Army in the early 1900s, not concrete, but they've made big slabs to collect dew on the top of Green Mountain as a source of water, because they really have none. There are now 2 desalination plants, luckily, one of them run by the US, one of them run by the UK. It is a UK overseas territory. This is where we are here with the Mid-Atlantic Ridge running through. It was taken over by the British when Napoleon was exiled to St. Helena, and they didn't want the French to come and rescue Napoleon, so took over Ascension. And there are around 800 inhabitants. None of them can legally stay there unless they have a job. So there aren't any kind of indigenous people from Ascension Island, probably because there's no water and very little plant life there. The sailors that used to go through there would drink the turtle blood as they went through as a way of getting some fluid as they went past. It's got a very interesting history. But the reason we care about it is the rock in the middle of the ocean. But it's actually strategically very important for both the UK and the US. There are lots of space observatories or telescopes on the island. There are key cables, transatlantic cables that run close by, and it was also very important during the Falklands War. It was a staging point for the British Air Force on their way to the Falklands. So it's strategically important. There's not a huge number of people, but it is very, very remote. So St. Helena is the closest landmass, more than 1,400 kilometers away. So if an eruption happens, they are quite on their own. Geologically, it's also incredibly interesting. It is only 100 kilometers from the mid-Atlantic ridge, but isotopically, it's got an ocean island signature, not a mid-ocean ridge signature. So it looks like we're tapping some anomalously enriched mantle here. Unlike Hawaii, there's no kind of hotspot track or anything like this. There's no evidence for elevated mantle potential temperatures or 3 helium suggesting primordial mantle. So it doesn't look like a mantle plume of a kind of traditional sense. It looks more like there's some weird, slightly wet, I suggest we're tapping a wet spot rather than a hot spot in the mantle, that's produced some slightly more voluminous volcanism than we would have classically expected. On the island itself, everything that's shown in green and grey are mafic centres, mafic lava flows, mafic scoria cones, and they kind of form a ring around the outside of the island. Everything in blue are felsic, explosive and effusive eruptions. And we've separated these into 2 main centres, the central felsic complex and the eastern felsic complex. The eastern felsic complex is slightly younger than the central felsic complex, but the oldest subaerial unit that's been dated is only 1.1 million years old. So it's young. It probably started to grow close to the mid-Atlantic ridge between 5 and 6 million years ago. So we've got kind of a little bit of history, but actually all of these eruptions that we see the deposits from at the surface are all less than 1 million years old. And it does have a huge range of eruptive styles. Pretty much any style of eruption that you can think of, we have evidence for in this little 12-kilometre wide island. We have lots of mafic lava flows with levees. We've got scoria cones plus scoria cone collapse deposits. This is Richie Brown from Durham University. So this is the normal scoria, and then we've had the scoria that has slid down on top of it. We've got extensive fissure systems, and Rebecca Winstanley, who I co-supervised her PhD, worked extensively on this letterbox system where we've produced these fissures and lava flows that have come out through. And we have lots of scoria cones that have kind of peppered the landscape all around the margins of the island. And then we have a lot of felsic volcanism. We've got felsic domes. This is White Horse that's produced these kind of trachytic to rhyolitic lava domes. And what was surprised us when we first went in 2014 was the pure number of felsic eruption deposits. So there are more than 60 that have happened in the last 1 million years. Katy Priest led the campaign to date these, and there are a huge number, especially given that this is not really something that has been considered a risk or a hazard. We don't see any change in the eruptions over time. There's no suggestion that this won't erupt again. So there's very much potential for felsic and mafic eruptions in the future. In terms of what they look like, they are silica undersaturated, so kind of transitional. They're not quite up in our Canary Islands composition. And quite interestingly, there's no clear daily gap, even though he daily visited the island, and it was one of the places that he used to suggest a daily gap. But when we look at the compositions, they do kind of trend all the way through from basalts through to rhyolites. And this variation that we see here, we think is like reflecting changes in source characteristics. But again, this hasn't been worked on in a huge amount of detail, and I think there's quite a lot more that could be done to look at how the source has changed over time. I've got some samples of a drill core that goes all the way through the volcanic edifice that I'd like to work on in the future. But what's very interesting here is that whilst we have this huge range of compositions in a really small spatial area, only 12 kilometres wide, most of the rocks on Ascension Island, most of the magmas are formed by simple fractional crystallization. And that was quite a fun 2 years, working out that they all just sit there and fractionate. And they don't interact very much, which is kind of tricky, because one of the ways that we can look at getting timescale information is by having a process that changes the composition of the crystals and gives us lovely zoned crystals. Ascension does not have nicely zoned crystals. Quite disappointing. However, there are a few eruptions that do have evidence for interaction between different magmas. And the one that I want to talk about today is the mingled fall deposit, which is found in a few places across the island. We know it's roughly 500,000 years old from argon-argon dating. And it starts off with an initially hydrovolcanic sequence before having a mostly pumiceous dominated fall deposit that then sharply transitions into a mafic dominated deposit. And so we go from having these pumice clasts that have physical evidence of mingling on a macroscopic scale to scoria with fragments of pumice also included within them. So we know that there's some mingling. We know that two different compositions, at least two different compositions of magma have come together. This has happened once before, and we know that they're being produced in similar areas. So this could be something that could happen in the future. Now, this is probably, I think this is one of my last scatter graphs, because I have tried to cap the number of element graphs that I put in the talk. Ultimately, what I'm trying to say is that the pumice, which are the blue areas here, have a relatively restricted composition in terms of their crystal cargo, whereas the scoria have a range of compositions. The scoria glass is a trapite. That doesn't really make sense. The melt inclusions from crystals within the scoria are also rhyolite. Doesn't make sense really either. Something's going on. So scorias have the scoria samples, which were deliberately picked to have no visible evidence of mingling, have crystals like quartz and phosphorus. They're just kind of a mishmash, which is a bit weird. Whereas the pumice have kind of the minerals and the melt inclusion compositions that we'd expect to be typical of a rhyolite melt. So I'm going to put that aside. The question we might want to ask if we think if this might happen in the future is, where did this mingling happen? So we analysed the melt inclusions, looking at their water and CO2 concentrations to give us an estimate of the depth that these melt inclusions were trapped at, if we assume that they are volatile saturated. And these crystals were growing, even in the rhyolite, at around 12 kilometres depth, which at Ascension, that's the moho. So we've somehow managed to make rhyolite at the moho, and we somehow managed to have scoria with quartz in. This eruption was interesting to look at. We've also recently submitted a paper on the zircons that we've extracted from both the scoria, the pumice, and there are some really weird plutonic enclaves that I'm not going to go into in too much detail, but we've extracted zircons from these that Jamie Scarrow has been working on. And the volcanic samples are all in orange, the plutonic are in red. And we can see that there's a peak in zircon ages, absolute ages, around in line with the eruption age and the carbon work. Fine, we know that crystals were sitting there forming, and then within the resolution of our uranium lead dating, so within a few within a few thousand years, there has been an eruption. That's fine. Whereas our plutonic samples don't really have a peak there. We can see some peaks that go further back. So we've got older periods of plutonics that were crystallizing over time. So the zircons don't really tell us about when mingling happened, but we know we've got crystals that have been inherited from different sources. Even volcanic zircons have peaks that exist prior to the kind of main eruption age. So we're inheriting crystals. And also the fact that scoria has zircon in the first place shouldn't really happen. So these scoria-hosted zircons, again, are picked up. This mafic melt is just coming through and taking all of the crystals that it wants. It's like, I'll have some quartz, I'll have some zircon, and yeah, I might fractionate a bit of olivine, but I'm just going to pick up as many crystals as I can from wherever it can. And if we look at the macrocrysts, we might say, okay, we know that two melts have come together. This has got to be the place where I see some nice zoned crystals. Unfortunately, no. There's not really any nice zoning in these crystals at all. But what we can see are some kind of plutonic glomerocryst-like plasts that have these kind of patchy zoning features within pumice and within scoria. And so we know that there have been plutonic crystals and plutonic plasts that have been picked up. So we've got kind of three components or more. We've got a rhyolite melt that's fractionating quartz. We've got a scoria or a mafic melt that's sitting there and ripping things up from everywhere else it can. And then we've got plutonic crystals, and we've got these coming from multiple different ages. So then the main way we thought to have a look at when mingling happens is to have a look at these glass textures, this so-called scoria glass that we analyze. So these are from chips of glassy material, glassy scoria, that were picked, again, to visually represent mafic material. And if we look at them, this area that's labeled B, that's kind of classic mafic scoria texture, microcrystalline, kind of a high brightness. But within this scoria class, we have areas of purely rhyolitic melts and quartz. So this is a little bit of rhyolite. And when I was choosing the spot to analyze on the iron probe, I'm going to choose the crystal-free, nicely vesicle-free areas to put my spot. rather than any of these that have got the microlite. So all of that rhyolitic glass that was in the scoria, that's just the selvages on crystals that have been ripped up into the scoria clasts. So we can see this contact between felsic melt and felsic minerals that have been ripped up into the scoria. And what's really interesting, so the scale bar here is 10 microns. The level of detail that we can see preserved on the contact between our rhyolite and our basalt here is really quite impressive. And it's not really that blurry. Not very quantitative, I'm afraid. So what would be really interesting is to measure profiles across here to create, to look at this diffusion boundary. However, fitting a spot on glass at a less than 1 micron scale is challenging, to say the least. So we haven't got those analyses. But when we compare it to experiments that have roughly similar compositions, it looks like this level of detail that we're preserving suggests that this is mingling happened between 1 and 24 hours before eruption, or at least 1 and 24 hours before diffusion could stop. If we assume the maximum, say, let's err on the side of caution, let's say it's 24 hours before this, after this mingling happened, before the eruption, that gives us an ascent rate of around 0.13 meters per second, or 3 meters per second for 1 hour, coming from 12 kilometers, which is where we know the magmas were stalled, which is pretty rapid. To compare it with the estimates from the La Palma eruption from 2021, based on the microlite studies, it suggests similar orders of magnitude, if not slightly lower. So there needs a lot more work. What would be great to do is to think about the bubble characteristics and think about the microlite textures here to put this in more detail. There's still a lot that can be done with this eruption, but it suggests actually that this would be something to worry about. If you had 24 hours of notice between unrest perhaps starting and needing to get 800 people off this island, that's not very much time. Planes aren't on the island at all times. In 2014 and 2015, there were 2 flights a week from the UK, from the Air Force Base, and it takes about 12 hours to get there. It's slightly faster from the US, but it's still a challenge. And that's assuming that as soon as this mingling happens and the ascent begins, that we would be able to detect this geophysically. I'm not saying that that's necessarily the case. We could have much less notice. There's also currently no monitoring on Ascension Island whatsoever. So you would be relying on far field or far away seismometers. There are some along the Mid-Atlantic Ridge. In fact, there might be one seismometer on Ascension Island as part of a wider network, but there's no monitoring going on the island at all at the moment. So even if there was geophysical unrest, you might not necessarily pick it up. So yeah, that was interesting. And what we were able to look at these timescales of ascent based on this mingling textures. What we don't know are the ascent rates for these eruptions where we don't have evidence of mingling happening, but there is a risk that they could be ascending on similar timescales because they're more alkaline, they're slightly lower viscosity. There is a lot more that could be done with the work on Ascension Island. But I'm going to leave that there and move to Volcan Puyehue, which is this stratovolcanic edifice here in southern Chile. Changed tack completely. We're no longer looking at intraplate volcanism. We're going to think about arc volcanism and the relationship between magmatic stress states and the timescales of ascent. So we're fairly happy that in a compressional regime, sill formation rather than dike formation is favoured, whereas in an extensional regime, dikes are more easy to form and we favour kind of vertical ascent of magma. And this comes from well, lots of work that has gone on, but Georg Zellmer suggested it in one of his papers that says, you know, in regional compression, we'd expect longer durations of magma residence in the crust, whereas in extensional regimes, we would expect shorter durations of magma residence. And I'm guilty of this too as a petrologist. I'm like, oh no, there's differences in the crystals. That must be something to do with stress. And it's this kind of ephemeral stress that we're like, yeah, there might be changes. And so the reason that we're excited us to work in this region in Puyehue-Cordón Caulle, just quite far south of Santiago, is that there's been previous work that's been led by Luis Lara to identify 3 different regions or three different areas that are in different stress states. So Puyehue-Cordón Caulle is a stratovolcanic complex, but to the north and to the south, there are lots of these monogenetic vents, which are shown by the black dots, and their small eruptive centers, which are shown in the green. So the Puyehue-Cordón Caulle is in relative compression, whereas these northeast aligned Carán Los Venados is in relative extension compared to the regional stress state. And then we have this Puyehue fault system, which runs through Puyehue, where some centers are aligned directly on top of, so they're suggested to be in relative transgression. So we've got three different areas within a very small region that should have the same mantle soil characteristics, and they do. They should have the same physical properties. We looked at only the basalts and basaltic andesites. So the thing that should be causing the differences in timescales could be the differences in stress state. So we tried to look at this one small area to remove lots of these other variables that could be introducing differences in physical properties and ascent to kind of narrow it down. So some more gratuitous field pictures, because it's never a bad thing to look at volcanoes on a Friday afternoon. This is Puyehue-Cordón Caulle from the river valley. It has basaltic andesites that form Volcan Puyehue here, but it also produces dacites and rhyolites, and what we can't see just behind this hill is the lava flows from the 2012 eruption that produced obsidians, and is identified as being in relative compression. But it also, as well as the regional stress state, it also has a large volcanic edifice, so that will have a loading effect on our crust as well, which the other centres don't. Carán Los Venados is a series of monogenetic cones to the north of Volcan Puyehue. The most recent eruption was in 1979 from Volcan Mirador, which is the lava flow is shown here. Surprisingly vegetated, having gone from the lovely Ascension Island, where things could be 1 million years old and you can still just walk across them, to southern Chile, where things were 50 years old and you had to dig the soil off the top of. That was a bit of an interesting change of pace. And these centres in Carán Los Venados are thought to be in relative extension, and so it was suggested that these should have the shortest timescales of magma residence and ascent, because they should be able to ascend more easily. We've got lots of evidence for multiple eruptions since the deglaciation happened. We have lots of lovely full deposits here that we could sample as well. The southern monogenetic centres that are aligned on the Puyehue fault system were less nice to sample. This was kind of mostly what we had to deal with. But they do form little discrete monogenetic centres and spatter cones that we could collect samples from, and has the suggestion that they're in kind of trans tension, but interacting also with the Puyehue fault system. So there was this kind of working hypothesis based on the stress states, and we wanted to test that by getting diffusion timescales from all three of these different centres. What you'll notice is that only one of these samples has a nice gradient, compositional gradient on the crystal. Again, the crystals have decided to foil me, but there are systematic differences in texture. So from the samples from Antecura, those that are lying north-south in this relative, on top of the Puyehue fault system, we see these kind of glomerocrystic blebs of olivine and feldspars, and variably they have some slight zoning preserved within them. The samples that we took from Volcan Puyehue have lovely olivines, which have this nice normal zone, high iron rim around the edge, and those are nice. We like those ones. We can do diffusion modelling on these. The samples from Carán Los Venados in relative extension all show these kind of classic skeletal or hopper morphologies, which are evidence of really high degrees of undercooling, really rapid crystal growth. So whilst there might be a bit of zoning here, we can't really do much with this because this is not behaving in a way that we very well understand. So the kind of extensional regions have textural evidence, but not quantitative evidence that they have had the most rapid ascent and produce these lovely crystals. So can't quite get quantitative timescales for each of these three regions, but we can at least get timescales from Puyehue. And in an ideal world, we'd have our diffusion model, which is the red line, and our data, which is in purple. and it would be like this, and we'd be very happy that what we're modeling is appropriate to this zone that we've extracted the compositional profile from, so going from the rim through into the crystal. However, probably about 50% of the crystals that we extracted from Puyehue had profiles that look like this. So if I just did the standard diffusion modeling, 1D isothermal diffusion modeling, my model would look like this green line, and my data would undershoot at the kind of the elbow here. That's not great. We might go, oh, it's not that much difference. It's not a huge you still get a time scale, and that would give me a day. It's not very much. But the fact that they systematically do undershoot at the kind of the elbow of the data suggests that we've actually got non-isothermal diffusion, and this crystal is growing at the same time that diffusion is happening. And so our simple 1D approach is not appropriate here. If we wanted to, and if we had the data available, we could try to model the growth and diffusion at the same time, but we didn't have access to the melt liquid line of descent because we don't actually have any melt left anymore. It's all crystalline. So instead, we decided to model through the section that we were pretty sure was just diffusion, and then ignore the section that would be more affected by growth. And so all of these timescales, therefore, are maximum timescales. If we were able to couple in growth and diffusion, it would reduce the timescale that we've actually modeled. But at least this way we could be consistent. This feature has been identified by other workers, and it's commonly seen in lava flows. So we were aware of this. We worked on lava flows from New Zealand that have this kind of longer timescales for this kind of poor fit to models. And so we deliberately sampled the rubbly tops of lava, so things that should have cooled fastest, because actually, clearly, diffusion is happening even when the lava are flowing. It's hot enough that diffusion can happen and the crystals are growing. And yet, even in these rubbly lava tops, we're still seeing this effect. So actually, whilst diffusion is a really powerful tool and really relatively easy to apply, we're looking at grayscale images and a couple of probe points here. That's not super expensive to collect. You have to be really careful about the methods that or the locations that you apply it to. So someone asked if it would be possible to do this on some of the Columbia River basalt lava flows, and all you're going to get there are timescales that are not relevant to subsurface. It would be how long has it been cooling for in the lava flow rather than anything else, and deconvolving that would be tricky. So for the samples where we were fairly happy that we could either remove or ignore the section of the crystal that's more likely to be affected by growth, or we had a really lovely fit, we could extract timescales. There were 5 from the Antikythera, those along in the north-south alignment, that all had less than 10 days. So that's all of the orange ones here in terms of ascent starting and diffusion stopping. They all have evidence for growth and diffusion occurring, so it's likely that these timescales are recording ascent and growth during a lava flow. The Puyehue samples, there were 2 different samples, hence the 2 different purples, are all less than 57 days, but the majority are kind of less than 15 days between ascent starting and diffusion stopping. So from 5 timescales from Antikythera, it's not really convincing. However, it does suggest that the Puyehue samples, those in relative compression, have slightly longer ascent timescales than those from Antikythera, especially because most of these 10 days is likely to be cooling within a lava flow. But we definitely need to resolve this more. And there were no resolvable timescales for Coran Los Venados, but we see those textures that are evidence of high degrees of undercooling and rapid ascent. So there's kind of some quantitative data that suggests that, again, that those areas in relative compression have longer ascent timescales than those in relative extension, but we weren't able to kind of fully constrain this. And so it's kind of non-conclusive, but still supportive of this kind of model. And I think there's lots more work that could be done to try and think about how we can extract quantitative timescales from all of these samples to then link it to stress states. And that's not even considering are long-term stress states representative of the stress state during ascent. There's many things that there could be more work done on. Again, the question comes that we're still only looking at around a few weeks of ascent timescale, and if that few weeks is geophysically detectable, again, we don't know. For the monogenetic centres, whether they're in extension or aligned on the Lacinier fault system, we're expecting timescales that will be much shorter, perhaps only a few days of warning, if that. And so this is a real risk, or a real something that really should be considered when we're planning for volcanic risk in these areas in the southern volcanic zone, where we have quite significant changes in their stress state based on the alignment of these volcanic centres. So I've chewed your ears off for long enough. So what? Are they actually useful? I've pointed out lots of ways that we don't know things, but actually timescales from crystals and glass, I would say, are useful. We can actually extract human relevant timescales, things on the order of days to weeks, from eruptions that are hundreds of thousands of years old. We don't have that possibility with many other techniques. If we limit ourselves to just studying historic eruptions where we know how much unrest there has been, we know how much geophysical kind of signals we can detect, we will lose a whole heap of understanding of past eruptive processes, past eruptive timescales. So by looking at the crystals, we can expand the kind of our knowledge of timescales of magmatic processes and volcanic processes to allow us to be better prepared for future volcanic events. Ideally, well, not ideally, if we're being really simplistic, we would expect that volcanoes that are in compression, we would have more warning, and volcanoes that are in extension, we might have slightly less warning because ascent would be more rapid. That's a huge generalization, and I think it's quite a good straw man to think about pulling apart. And we'll have, there'll be lots more variables that will interact much more complex ways. However, crystals can't see everything. There are some changes in magma withdrawal dynamics that are invisible. The mingled fall deposit on Ascension, it happened so quickly the crystals couldn't respond to it. They just, the timescales of mingling were much shorter than the timescales of crystal growth. And ultimately, we need to work with experimental petrologists to refine the diffusivities. There's a lot of uncertainty on diffusion modelling, and we need more experiments to understand this, to be able to put better estimates on these timescales. And the big question is, it's great, we can look at prehistoric eruptions to look at unrest timescales or ascent timescales, but we don't know actually how that relates to geophysical unrest. And so we need to use the historic eruptions as kind of this key to understand what the crystal changes are recording and what the geophysical data sets are recording, to then think about how we can interpret the crystal information from time eruptions when we didn't have geophysical data. So there's still a lot of work to do. There's still a lot more experiments that we need to do to understand and constrain these better, but hopefully convince you that there at least is something nice. And if all else fails, we get to look at pretty crystals with nice stones, and that's a good thing. So I'll stop there with some fieldwork by horseback from on the Volcan Puyehue.
Thank you very much, Katy. Does anyone have any questions for Katy? What's the historical record like on the Ascension Island? Are there many reported? I guess
no, there is none. So the last eruption was 500 years ago. I think there were records of people sailing past around 500 years ago that suggest that there was smoke, but we don't have any witnessed eruptions at Ascension Island. No, so yeah, that's the challenge. It was really impressive. So Katy Priest, who's now at Swansea, we were told about flows that were hot underfoot by people that live there, and they're not. It's just that you get out of the wind and suddenly it feels quite warm there, and like some lava tubes were hot, but again, just out of the wind. And so there was all of this talk, but Katy worked really hard to go through the historical records and go through shipping logs to try and work out what had actually happened. So that's it's a nice read. It's a geology paper from 2018. It's interesting, like, for that kind of connection between archival records of volcanic history and what you could resolve without an amalgam date. And I think so far it might be the youngest amalgam date that has been produced, which is quite interesting. It's a basalt, not very image. Yeah.
I was interested in that kind of truncated diffusion profile you have, where you said that growth basically disrupted the diffusion in there. So when this growth happens, well, is that when the magma is moving and cooling?
Yeah, so that's a good question. So one of the ways that we could tell that these were definitely growth affected is that in some areas of the crystals, you'd see, so the growth is related to the microlite formation, but we're still growing on the outside of the macrocrystal too. In some cases, this high iron zone, I don't know if you can see, some areas there's more iron and some areas there doesn't seem to be as much diffusion. And it's likely that these areas had feldspars attached to them, so the feldspar microlites have stuck onto them. And so where the zones aren't kind of nicely developed around the whole crystal, we know that the ascent and the iron diffusion only happened where it was in contact with the melt, and when you had microlites attached to it, attached to the crystal base, they'll use as a nucleation surface, it couldn't interact with that melt. So whilst we would extract the profile where it looks nicest, say for example there or here, actually know that probably there's been an effect where the microlites were also growing at the same time that diffusion was happening. So this is likely growing outwards into the melt at the same time that iron is diffusing in from the melt as well.
So I was just thinking for the Chilean example as well. So Puyehue erupted the day after the Valdivia earthquake. That was recorded earthquake in 1960, magnitude 9.5. So I'm just wondering whether you've got these timescales in the magma chamber, which if the area wasn't disrupted by huge catastrophic events like that earthquake, you maybe see a clearer picture between residence time and the tectonic environment. But I guess the question I was coming to is the major events like that, which will have just altered the stress field. How much do you think that disrupts this picture? Things like this be telling you something about events like that?
Yes, that's a good question. So we didn't look at any of the felsic eruptions. The 1960, 2011 and 1922 eruptions were all rhyolites, and they all have different physical properties to a basalt. So didn't look at them. It would be really interesting to have a look at them in more detail. I have samples. As far as I can tell, I did have a very rapid look at them. One day one had a bit of extra SEM time. They weren't really zoned. The pyroxenes weren't really zoned. But that's because pyroxene diffusion is much slower than iron magnesium diffusion in olivine, and it's also much cooler. So we want to find a mafic example that had olivine that was hot that might record timescales that are more similar to that. But that's also a really good question: is how do we? So the stress states for these areas are an integration of local tectonic earthquakes plus dike orientation. So it's a long-term stress state, but what we're not recording are how that stress state changes it on shorter day scale, day scales. I think it would be really interesting to have a look at to maybe more detail.
So that graph there, so when you've got a diffusion curve going on, I think it always has the same error function shape, whether it's isothermal or not.
Yeah.
So can you expand on where the discrepancies occur on that picture there?
So because this is only a half function, because we're looking at diffusion in from the melt rather than within a crystalline boundary. So this is the error function, and then this is not down here. So it's because we cannot fit the modelled data in purple with an error function, and so it's not. So we need to have kind of multiple steps. So we would model to here, and then we'd model this by trying to take into account the growth and diffusion at the same time.
Right, so the key thing there is you've got to have growth. You can have an isothermal, you'll have an error. You've got to have growth as well.
Yes.
I was thinking about the green game. Things in Ascension. So this, a common extrapolation from evidence of cooling is that this is somehow triggering an eruption. So any comment on evidence for that?
Yes, it is commonly incited. I would suggest it did definitely trigger this eruption, because we had to have the rhyolite formation. We suggest here, based on work compared to other Ascension evolved deposits, that the rhyolite is formed through partial melting of the gabbro. We cannot reproduce these compositions through just simple fractional crystallization. So it's likely that there have been, at the moment, there were quite a few mafic intrusions. We partially melted some of the gabbros at depth, although that feels quite hard to melt a gabbro. But we produced a rhyolite. That rhyolite probably wouldn't have erupted unless it interacted with the matrix that came through. The potential is that we have quite a lot of intrusive speltic bodies at depth in Ascension that just don't erupt because they're not triggered by this interaction. Given the timescales and that have to be very short to preserve these textures in the glass, I don't really know what else would have triggered this unless something triggered. Unless something triggered the basalt to interact with the rhyolite, and then the mingling is actually a function of a different trigger mechanism. But then that's kind of, you say this back, but yeah.
So what's going on in that? So,
Yeah.
you know, I'm going to be about the union and the Puyehue continental fragments of like part of the course of the
Yeah.
Is that something you're collaborators interested in?
Well, so we got a lot of zircons from a few eruptions to try and see if we could find, not necessarily just to look for old zircons, but they should be hanging around if they were there. And we haven't got anything that's beyond the lifetime of Ascension, whereas I think in Iceland they do have some quite old zircons. I don't see much evidence for the continental crust being here. We have there isn't a huge amount of recent seismic data. We've thought about trying to put a bid in to go and collect more, but I think it's quite a big undertaking to go and do quite a lot of shipborne seismic. But we know that there's this kind of core in the lower crust of plutonic material, but I suspect that has been established through the kind of 6 million years of volcanism rather than anything else. And there isn't anything that I've seen reported below Ascension that might suggest any continental crust, but there's still a lot of work to be done on it. So I've got all these drill chippings from through the whole edifice, because we're limited by just looking at the top kind of 5% of the volcano that's exposed severely. And it would be really nice to look at the radiogenic isotopes over time to see if we see any changes in the degree of partial melting or any changes in our source composition that might suggest, essentially dying on a 1 million year timescale, or whether it's actually been the same for the whole time that it's been erupting for the last 5 million years. So that's something I would like to,
Olivia, thank you again for your wonderful talk.